Alright, so today I will show how to solve the TwoSum problem in LeetCode, which I will read right now. So we're given an array of integers called nums and one extra integer called target, and we want to return the indices of the two numbers such that they add up to target. We might assume that each input array has exactly one solution, and we are not allowed to return the same element twice, and the answer, which will exist, can be returned in any order. So there are some examples here. So for example, we're given this array 2, 7, 11, 15, and a target of 9, and we see here that 2 and 7 add up to 9, and 2 as index 0 and 7 as index 1, so the valid output, so it's going to be 0, 1. But also, because we can return the answer in any order, the pair 1, 0 would have been also valid. In the second example, we have 3, 2, 4, and a target of 6. And we observe that here the pair of values 2, 4 add up to 6, 2 as index 1 and 4 as index 2, and therefore a valid output is 1, 2, or again equivalently 2, 1. So that would also been fine. Would have been fine. So, and then we have the third example with a repeated element 3, 3, and the target is 6. We could consider 3 at cell 0 and 3 again in cell 0, which are this element twice repeated would add up to 6, but we know from here that we cannot use the same element twice, so 0, 0 or 1, 1 is not valid. We can only add up these two elements together, which respectively they have the first one index 0 and the second one index 1. Some constraints here which are always useful to read. So the array size is between 2 and 10 to the 4th. Every element is between minus 10 to the 9 and 10 to the 9 included, and so is the target. And again, this final remark here that only one valid solution exists, and the question ends with a follow-up question whether or not we can design an algorithm less than O(n) squared time complexity. So now I will show I will show how to design both the naive algorithm, which has complexity O(n) squared, and a more optimized one, which will have linear complexity. And then I will implement this in C++. Now I will design the solution, both naive and slightly clever one, for the TwoSum problem. So for the TwoSum problem, I will summarize here the relevant bits of the assignment. So in the TwoSum problem, we have an array A of n elements, A0 up to an-1. We are also given a target value t. They're both integers. So one is an array of integers, the other one is just an integer in the given range from the problem. And we know that there exists a unique pair up to order, pair ij, with I different from j, such that ai plus aj is going to be equal to the target. And the goal here is to return, again up to order, is to return the pair ij. Okay. Now, to solve this problem with a naive approach, So we just have to look at this formulation of the statement of the problem. So if we just look at this, okay, this proposition here is telling us that all we have to do, because the pair exists, and by skipping just the ones that are equal, so the equal indices, we just have to find the pair that will, such that the values of those indices will adapt to the target value t. Now, just to make the naive approach slightly clever, we make just an observation. So if ij is not a solution, then ai plus aj is not equal to t, and this implies that aj plus ai is not equal to the target, and therefore obviously this implies that ji is not a solution. What this allows us to do, this observation here, what this observation allows us to do is just to write a for loop where the iterations, they're going to be slightly less than the total of n squared that we could do until we find the right solution. So the naive approach can be essentially represented using the following pseudocode. So for I equals 0 to n minus 1, and for j equal I plus 1 to n minus 1, if ai plus aj is equal to the target, then we just return the pair ij. Now, let's observe that this, so first of all, the fact that I needs to be different from j in the pseudocode is essentially taken into account by the fact that the j will always start from an index different from the current I. And the fact that if we, in an iteration, so if in an iteration ij, we don't have a solution, so then if we swap the two indices, we still don't have a solution due to this proposition here. This is taken into account by the fact that we only iterate from I plus 1 onwards. Now, the complexity of this, so the main operation done in this pseudocode is essentially this pair of addition and test for equality. And we can assume that the cost of these two together is going to be O1. So therefore, all we have to do to calculate the time complexity, which I'm going to denote with C naive of the input, given the input size of the array n, this is less than equal than the sum from I equals 0 to n minus 1 of how many tests do we have here in the worst case? Well, we have to do all of them, so for every j, and they're going to be exactly n minus I minus 1. And we can see that this is going to be equal to n minus 1 divided by 2. And therefore, this yields that C naive of n is equal to an O of n squared, as expected. So we have this, this thing here. Okay. Now, if we want to write a slightly clever solution, the key observation is to take this proposition here, underlined in blue, which I will rewrite again, and just make a tiny bit, just observe a little consequence that comes out from this proposition. So we know that there exists a unique pair ij, again up to order, with I different from j, such that ai plus aj is equal to this target value. Obviously, this implies that there is an index I for which there is an index j, again still with I different from j, but in particular there is an index j such that aj is going to be equal to the target minus ai. By looking at this implication of the condition, the way to look at this is the following. So suppose in this we have this the input array, and we are iterating. So this is the input array, and we are currently, say, at index I, where we have value ai. Now, if this I is the left index of the solution, then by this consequence here, we must have an index j where the actual value corresponding to the solution, to the right index of the solution, is aj, which can be easily retrieved or inferred anyway, but by simply subtracting ai from the target value. So say aj is going to be here, the index j. So we know that aj must be equal to t minus ai. Now, from this drawing here, we need essentially to take into account, or just to keep track for every element, what is the corresponding index. So in a way, we're encoding the inverse mapping that naturally an array would encode. So an array would encode a mapping from indices to values. So an array, a normal array, is a mapping from, say, indices to values. So given I, it gives me ai. We want to do, say, the inverse of this. So I'm gonna call, for obvious reasons, this capital H. H wants to encode essentially a mapping from values to indices. In other words, given ai, it wants to give I. The most common way to implement these kind of inverse mappings are hash maps. So I'm going to use a hash map now to implement this inverse mapping, and then I will show, by analyzing the corresponding algorithm, how this actually speeds up the time complexity. How does it lower it? So, okay, so first of all, I'm going to declare H as a empty hash map, of int, okay? And then just like the previous code, pseudocode, I'm going to iterate from I equals 0 to n minus 1. And here I'm going to do a test to see whether or not we have the corresponding t minus ai key in the hash map. So if h of t minus ai is not empty, then we return the pair I h of t minus ai. If it does not, if it is not empty, what we want to return, what we want to do in this case, is to make sure that we are keeping track of this current value ai and its current index. So the reason for doing this, it's because of this diagram here. Because maybe we have a state where we actually haven't met yet the element ij that adding up to ai would lead to having the sum equal to the target. Therefore, what we want to make sure is in case later on we come across the corresponding AJ, we are still able to retrieve the index AI. And to do this, we just store this in the hash map h of AI. It's going to be equal to I. Now, we can make the assumption, for example, in the C++ standard library, if you go, for example, in the unordered map, which is going to be the one I will use in implementation, the documentation will tell you that the average, so any average running time for insertion, fetch, and retrieval is going to be, so I'm going to call this TH, just to take into account any cost of an operation in a hash map, at least the relevant one in this pseudocode. This one is going to be on average 0.1. Okay, average. Okay, THAVG. Okay, therefore, what we can put as an estimate for the running time, I'm going to call this C opt given n. So for every iteration, we do a set of hash maps operation. In one case is a search, a retrieval, and in the other case is just an insertion. So, but this is done essentially for every iteration, either one or the other. So we can say that the C opt of n is going to be essentially n times TH average, whatever this cost might be, which we know is going to be n times 0.1, which we know is going to be O of n. And therefore, this is an optimal algorithm. Well, a faster algorithm. This is faster in time, obviously, but in terms of memory, the naive solution, memory, for the naive one, we have a 0.1 memory consumption. Why? Because we're not using auxiliary variables or auxiliary memory in any way. But for the optimal one, the one with the hash table, obviously, because we have to store all the values being encountered so far, and in the worst case, we are going to keep adding up to n-1 values in the hash map, and then at the nth iteration, we will just retrieve the corresponding value. This is going to be essentially a worst case scenario of n memory consumption. So the naive solution has obviously a better memory consumption, but the optimized one with the hash map has a worse memory requirement. So now I will implement the optimal algorithm in the optimized algorithm in C++, and I will show you how to implement it then. Alright, so now I will show how to implement the solution of the TwoSum problem using a hash map, just like the pseudocode I wrote earlier. So first of all, I will declare this hash map that in C++ is implemented as an unordered map, integer keys, integer values. I'm gonna call this h just to follow the same notation I wrote in the pseudocode, and then I will iterate through all the elements of the input array. For int I equals 0, I less than nums.size plus I, and I'm gonna test if the hash table contains the key target minus nums I. So if h of target minus nums I, if h.find target minus nums I is different from h.end, so this means that this find here won't return the final iterator, which is what the find would return if there's no such a key. But if there is one, I'm going to return a std vector of integers of I and h of target minus nums I. If I don't reach this if statement, then I'm gonna store in this hash map this current value as a key and its index as value. And this is because maybe later on I might find a corresponding AJ that added to this AI will return the would adapt to the target value. So I'm just gonna do h of nums I equal I, and then I'm gonna return, because otherwise it's gonna give me a compiler error, just an empty array. Return std vector of int with nothing. Now, first of all, let's run it on the simple test cases to see if it works fine. Perfect, all the test cases are passed. Let's submit it just to see the running time. So let's submit it. And there you go. So this is the solution with the hash maps for this problem. Thank you for watching.